In this video, I'll start talking about the rectangular waveguide, and I'm taking Pozar's microwave engineering book as reference. So let's have a general idea about what a rectangular waveguide is. So all of this is one piece of metal. So from the start, we know that TE₁₀ mode can propagate in this as it's only one conductor. This piece is metal and inside is filled with some sort of dielectric material having properties mu and epsilon, the permeability and the permittivity. It's a convention that we put the longer side on the x-axis and the shorter side on the y-axis. So always A is greater than B or equal. I'll start talking about the TE mode. So in TE, we know that Ez equals 0, and then we have all the other 5 components. We have this matrix that we're going to use and get some components from it later on. We'll start by the reduced form of Helmholtz equation. So our equation states that the second derivative in x plus the second derivative in y. Also, there was a second derivative in z, but that was reduced to negative beta squared, and then we have kc squared hz of xy equals 0. So this term has both the k squared and the beta squared. So on the side we could write that kc squared equals k squared minus beta squared. In the parallel plate waveguide, for example, this term was 0 as there was no dependence on x, but here we have dependence on x, so it's definitely not 0. So this is only a function of x and y, and the hz capital of xyz would be just this small one, and the dependence on z is just this exponent e to the power negative j beta z. Okay, to solve this differential equation, we're going to use the method of separation of variables by letting hz of x and y, it's only a function of x and y, so we're going to say it's a function of x times a function of y. And then substituting in this equation, we will get d squared x capital by dx squared times y of y plus d squared capital Y by dy squared times x capital of x plus kc squared x capital of x times y capital of y equals 0. We're going to then divide by xy. So this is going to be 1 over x capital d squared x by dx squared plus 1 over y capital d squared y capital by dy squared plus kc squared equals 0. So this is a constant, and this is a function of y only, and this is a function of x only. So in order to satisfy that everything equals 0, this must be a constant, and this also must be a constant. So the book defines the constants as d squared by x dx squared plus kx squared x equals 0, and that means that this part is just negative kx squared. And the same thing for this part, which will be negative ky squared from d squared y over dy squared plus ky squared y equals 0. So this equation is then kc squared equals kx squared plus ky squared. We will then find that the general solution for hz of x and y equals a cosine kx of x plus b sine kx times x I meant, and then all of this times c cosine ky of y plus d sine ky y. So this part is just x capital of x by solving this equation, and this part is y capital of y from the other one. And then we have our boundary conditions that the tangential electric fields are equal 0. So if you go to our waveguide here, we will have at this side we have e of x, e of z, and e of y. we are talking about TE mode, so this is already 0. And then our tangential component is EX. So EX of X and 0 and Z, and also EX of X, B, and Z equals 0. So we have here at this side and here at this side. And the same thing goes for the EY. So we have EY in here, EY in here. This is the tangential component, and the EZ equals 0. We have EY of 0, Y, Z, and EY of A, Y, Z equals 0. So let's substitute there, and let me just rewrite them real quick. I wrote them, and then let's substitute our boundary conditions. But first we have to get our EX and EY. Now let's get EX from our matrix. So here we have EX. Let's just write it at the top. So EX equals J over KC squared times. So this part is 0 already, and this part is times dEz by dx, and dEz is 0, so this part is 0 also. And then we have just negative omega mu dHz by dy. And then for our EY, we have J over KC squared times beta times dz, which is 0, and then we have 0, 0, and then we're left with omega mu dHz by dx. I got the equations. Now let's substitute and find the EX. Okay, so we'll start by writing EX equals J over KC squared, and then we have omega mu, so just write here omega mu and then the negative part, and then let's derivate it. This whole part is constant with respect to y, so we'll just write A cosine kxx plus B sine kxx. And then the other part, let's derivate it. The derivative of cosine is negative sine, so we have negative C sine negative C ky sine ky y plus d ky cosine ky. So that is just negative j omega mu over kc squared times ky a cosine kxx plus b sine kxx negative c sine ky y plus d cosine ky y. And then do the same thing for the EY. We'll find that EY equals j omega mu over kc squared, and then this time is kx, we're derivating with respect to x, negative a sine kxx plus b cosine kxx times c cosine ky y plus d sine ky y. Now let's substitute in our boundary conditions. So it says EX equals 0 at Y equals 0. So at Y equals 0, this term will be 0. And then we are left with this part. We'll get only D from this part, as cosine 0 is 1. And then it will be D multiplied by this whole part. And it needs to be 0 and satisfy for any X. So that means that our D equals 0. And then at substituting at Y equals B, so let's see what happens at Y equals B. So at Y equals B, EX of X and B equals negative j omega mu over kc squared times ky a cosine kxx plus b sine kxx times negative c sine ky times b, and that should be equals 0. So that means this part is 0, and c can't be 0 as we have a field in EX, so that means sine ky b equals 0. So ky b should be n pi. That means ky equals n pi over b. And doing the same thing for EY, we could find that kx equals m pi over A. Now let's substitute in our main hz of x, y, z. It will be a mn cosine kxx, which is m pi x over a cosine n pi y over b. And then don't forget the propagation term, which is e power negative j beta. Then substituting and derivating to get the other terms, you will find that these are the other field components, and as we know, Ez equals 0. We know that beta equals square root k squared minus kc squared. And we know that kc squared equals kx squared plus ky squared, so that means this equals k squared minus m pi over a squared minus n pi over b squared. So beta is real when k is greater than kc. And then to get the cutoff frequency, we're going to say that k equals kc, and that means omega root u epsilon equals square root this whole thing, and then omega is just 2 pi f cutoff. So we could say that fc of mn equals 1 over 2 pi root mu epsilon, and then m pi over a squared plus n pi over b squared. And then we have a note here that says the mode with the lowest cutoff frequency is called the dominant mode. Because we have assumed a is greater than b, the lowest cutoff frequency occurs for TE₁₀. That means m equals 1 and n equals 0. So a is bigger, so that means this whole term is smaller than this whole term. And fc of 1,0 equals 1 over 2a root mu epsilon. And also, there is nothing called TE₁₀ mode. Let's get the wave impedance, which is ZTE equals EX over HY. You will find common terms that will be cancelled together, which are the cosine m something, and then sine n something, and e power negative j beta z. All those terms. Okay, let's say here. This term is similar to this term, and this term is similar to this term, and this term is similar to this term. So we're just going to put this thing over this thing. Other things will be cancelled, which are j n pi kc square b. So that leaves us with ZTE equals k eta over beta, and that is just root mu over epsilon. And it's the intrinsic impedance of the material filling the waveguide. And then to get lambda g, that equals 2 pi over beta, and lambda g is greater than lambda as beta is smaller than k, as lambda equals 2 pi over k. So because beta is smaller than k, that means lambda g is greater. And then the phase velocity equals Vp equals omega over beta, and that is greater than omega over k, which equals omega over omega root mu epsilon, which is 1 over root mu epsilon, which is the speed of light in the medium. So that means Vp will be greater than the speed of light in the medium. Finally, let's just get kc and beta for the TE₁₀ mode. So kc equals root m pi over a squared plus n pi over b squared, and equals 0, so that means kc is just m pi over, and our m is 1, so kc equals pi over a. And then that means our beta is going to be k squared minus pi over a all squared. So that's it for this video about TE mode in rectangular waveguide. Check the next videos for TM modes and other things in the rectangular waveguide.